All right, class, welcome back. So this is Tuesday's lecture for the 13th week of class. We're still in chapter 7 on the energy of extended systems. So we're starting with section 7.3, potential energy of neutral pairs of atoms. And what this is going to build on is that ball spring model of matter that we've been talking about since really chapter 4. All right, so let's recap what we know. So in chapter 6, we talked about that the potential energy between two charged objects is equal to 1 over 4 pi epsilon naught. This, of course, was discussed after we went online, so feel free to go back to week 12's lectures to review this. So we have Q1, Q2 over R for two charged particles. Okay. Now, in chapter 4, we have talked about that there are spring-like interactions between atoms. And that's, of course, an exaggerated bond that I've drawn right there. And we've said that these interactions are electrical in nature, meaning that we're dealing with an electromagnetic force between the two of them. And we also have talked about, spring model of matter. And we have also talked about that atoms in their natural state are electrically neutral. Meaning the number of protons will equal the number of electrons, giving you a net charge of 0. Okay, so let's think about the then how electric potential energy relates to atoms. So if we have two atoms, so they're going to have positive nuclei because that's where all the protons live, and then they're going to have this little electron cloud surrounding them. So positive, negative. And if they're far apart, so these two are far apart, so we're not going to see any interactions. So no interactions via the forces. You know, even Darth Vader has to be kind of close to do that Sith death grip. If you're too far apart, no go. However, if you start to bring these two atoms closer together, something interesting happens. So now we've got these two these two nuclei. We've brought them closer together, and they've brought with them their electron clouds. So this electron cloud here is going to be like, hey, I see a positive particle right over here, and it's going to distort and try to get closer. Whereas this electron cloud is going to be like, oh gosh, I see another negative particle over there. Yuck, I'm going to distort in this way. So the electron clouds distort, and the two atoms will attract. So one electron cloud is attracted to the positive nucleus of the other atom. It's going to distort, making, as we will learn in chapter 13 of next semester, a little dipole. But that's a treat for later. For now, just know that they're starting to get close to each other. Now, however, if you push them even closer, they're going to start to repel because they can only distort so much. So start to bring them closer together, and they're going to attract. Push them too close, and they're like, no, too close for comfort. It's kind of pertinent to our present situation where, we like the people we live with. We like them. We're attracted to them. We want to be around them. And now we have all been pushed together really closely, and we're starting to repel those around us. There's just a nice distance that we like to have. All right, so this is not unlike the spring system. This is spring-like behavior. Come close to me, but not too close. So, and of course, to understand this in more detail, the superposition of electric forces, you really need to take a class in quantum mechanics, which I highly recommend. For those of you that are a little bit interested in quantum mechanics, we will, and also students at Northwestern, Physics 3 or Modern Physics will introduce quantum. And I, for one, am very excited to teach the class, and I would be excited to have you in it. All right, so we have now spring-like behavior between atoms. Okay. And just like real springs, this will work as long as it's not overly stretched or over compressed. Overly stretched, you break the bond. Overly compressed, other stuff happens. Okay. So, the approximate interactions, potential energy. So the potential energy for these atomic interactions is going to be equal to 1/2 K sub S, S squared, minus EM. And EM is this offset I told you about before. We're dealing with a real system. We know it's got a real offset. The potential is in the negative for atoms. We'll get into this in a little bit more detail in chapter 8, which is coming up next. So for an ideal system, looks something like this. We've got stretch, we have the spring potential between the atoms, and then we've got this offset with this negative energy well right here. Okay, now this is an overly simplified model that I have drawn, so overly simplistic. And really, all the models I'm going to show you are still going to stay kind of simplistic in this chapter, but I want to lay a nice foundation for you so that you could build on these concepts and understand physics in a little bit more detail. So, real potential energy cannot go to infinity for these atomic interactions. So in other words, and we know that electrons can become unbound. And so what I've drawn here is a bound state, or a completely bound system. So it needs to approach zero. We know atoms can lose electrons, so. All right, so instead we have something that actually looks more like this. So then you've got K plus U for one state, K plus U, K plus U, and you have your offset. Here it is. So I'm laying down foundations of ideas that we'll pick up in the next chapter. So E sub M tends to be a few eV. We'll see, take a better look at those numbers in the next chapter. And then if you were to have something up here, this would be unbound. These are bound. So it has states where things are bound and states where things are unbound. Now, we also have something else. We have something called REQ, or R equivalent. And this is the distance when U is at a minimum. So there is a minimum of potential energy. Okay, so this is the model I want you to keep in mind, and now we're going to update our potential energy equations for those atomic interactions. So the potential energy is equal to EM minus E minus alpha, which is a scaling constant, R minus REQ, quantity squared, minus EM. And this is actually U sub n because it's called the Morse potential. And REQ tends to be about 1 times 10 to the minus 10 meters. That would be the approximate diameter of an atom, and that's where U is at a minimum. And this equation describes this model. So the Morse potential is described by this model. All right, so that's the last thing I wanted to say about the interactions between atoms. And like I said before, this is just laying some groundwork that we're going to pick up more in the next chapter, and this is something you can continue to build upon. Of course, these are still somewhat idealized models, but it's a fun place to get started. All right, so we now have what we need to start going after understanding internal energy. All right, so let's consider a ball connected to a spring. Ta-da! There it is. All right, so now, if we model this particular system like a point particle, so point particle model, this becomes this. Well, if we're just dealing with a dot, then it can only have kinetic and only K and MC squared. It can't have any potential, so no potential, and no deformation. So problem, because this system, now, I mean, it could be the right model depending on what your question is asking, but we can see we've got some deformation going on. And we know that we've got some potential energy that might provide us something really useful that we need to know. So what we need is an extended system. So we need an extended system for ball spring. Then we can look at, let's say we've got two balls connected by a spring. They can move. We can look at all that deformation. It's fantastic. They can vibrate, and we can account for it, so we can deal with vibration. They can stretch. They could rotate. And as long as we're dealing with an extended system, so not a point system, but an extended system, we can go after all of these different types of energy. And these types of energy, these are examples of internal energy, energy that is innate to the system. And there are several types. Of internal energy, one of which is temperature. Oh, it's internal energy. And so we're going to be really building on the different types of internal energies. Okay, so internal energy. So we've got internal energy equals E thermal plus E rotational plus E vibrational plus E chemical plus, it can go on and on and on. So thermal, that would be heat, rotational, rotating, vibrational, vibrating, chemical, the food you eat is a part of your internal energy. But one thing to note, this is not a new type of energy. We're just expanding on a category. And it's really for convenience sake. So multi-particle systems, still just contain three main types of energy: rest energy, kinetic energy, and potential energy. Internal energy is contained within the rest energy. So we've been dealing with it all along, but we've not categorized it. So the internal energy internal energy categories are convenient for analyzing systems. So we do this because it makes our lives easier. We like to do things the easy way in physics. So one way to think about it, we know, like I said, it's a part of the rest energy. So the mass of the system is equal to the energy of the system divided by c squared. And so this is all the internal stuff, a lot of which is going to be mass. But for example, a hotter object is going to be vibrating with more velocity than a cold object. So this gives us greater insight into all of the energies for a particular system, even the idea of bouncing a ball. So now, if you were to do this with an extended system, the ball hits the floor, causing the atomic springs to compress and vibrate, generating heat before it comes back up. This is all a part of that system. So you want to make sure that you have vibrating springs in your mind going forward. All right, so let's talk about temperature. Temperature is, it's just such a cool thing. So this is a measure of the average random energy in a system. So we're going to do a very precise treatment of temperature in chapter 12 if we get there. That may be a little optimistic for this semester. But for now, we need to start thinking about it from the correct state of mind. So, setting up temperature. The standard temperature scale is kelvins. And it starts at absolute zero. And the degree size for Kelvin, so 1 Kelvin, is approximately 1 times 10 to the minus 23 joules. So just a note, degrees Celsius are the same size. They have the same quantity as kelvins, but the scale starts at a different point. So 0 Celsius is when water freezes. Which I think is 273 Kelvin. Okay. So now that we have a method of talking about how we measure temperature on a particular scale, let's start thinking about the temperature of objects. So temperature is the result of the vibrating springs of matter. So of course, my favorite experiment to do, take your 2 hands, rub them together. You'll see that they're getting hotter. It's because the atomic springs within your hand are vibrating more quickly, generating heat. So if you think about matter as being these vibrating blobs, so if we place a cold block of matter next to a hot block of matter, what's going to happen? These springs are vibrating back and forth furiously, and they're going to start hitting those cold springs over and over and over and over again. And of course, when you have a spring that gets hit over and over and over and over again, you can get it so that it is now in motion as well. All right. So, and eventually what's going to happen is these 2 objects are going to normalize to the same temperature. So things like to reach equilibriums. Now, how much energy is required to change the temperature varies by the material. So different materials require different amounts of energy to change temperature. So this is called heat capacity. So for water, the heat capacity is 4.2 joules per Kelvin per gram. Would also follow that this is 4.2 joules per degree Celsius per gram. And Joule measured it first. It's actually a really fun classic paper to read about how he first measured that. So Joule was a brewer. He made beer, and as a result, got very interested in temperatures. I love these stories. All right, so calculations using specific heat, they come right from the energy principle. So specific heat, which is how much an object wants to change its temperature, is equal to the change in thermal energy divided by m, the mass, times delta T, the change in temperature. So if you are using a C in grams, then the mass is in grams for C in grams. Of course, you could always unit convert depending on your needs. Okay, so delta delta E thermal, is the rise of internal energy. Which is really coming in the form of increased atomic K and U in those atomic spring systems. And C, as I said before, and I'm going to repeat, is materially dependent. If you know one C, you do not know all C's. You know one C. All right, and it's very, very, very useful because if you know the specific heat for a particular material, then the amount of energy transfer can be measured with temperature. So if you know C and delta T is easy to measure, you can go after delta E thermal, which is very hard to measure. So delta E thermal is hard to measure. This is easy. And this is doable. And if you know this, mass is also easy. Then you can go after something much harder. Okay. So let's do the classic example. So for those of you who have taken chemistry, this should be old hat. For those of you that haven't, which could be a few of you. So you stir 6 kilograms of water, liquid water, vigorously. You are just going to town on it, doing 38,000 joules of work. We're going to assume this is happening in a well-insulated container, so nothing to contribute any work. So well, you're contributing work, nothing else is, and it's not being lost. All of your work is converted to temperature. How much would you expect the water temperature to increase? So we have 6 kilograms of water, and we have put in 38,000 joules of work. Okay. So this is a energy principle system. So the change in energy of a system is equal to the work being done. In this case, we know that we're dealing with a thermal change, so we're going to use mc delta T is equal to the work being done. This is what we want. Delta T is equal to work divided by mc, which is equal to 38,000 joules given in the problem, 6 kilograms, or actually 6,000 grams, we need to convert it, times 4.2 joules per Kelvin per gram. And so we get that the change in temperature is 1.5 degrees Kelvin. So be careful with your units. Make sure you are using the right C for the mass and temperature that you're using. Now, it is possible there are specific heats that have been measured for Fahrenheit. Unless you're going to work with a Fahrenheit scale, do not use those specific heats. All right, so let's go ahead and do another example. All right, so you have a 400-gram block of titanium at a temperature of 550 degrees Kelvin. placed on a 700-gram block of nickel with a temperature of 275 degrees Kelvin. So the specific heat of titanium is equal to 0.544 joules per Kelvin per gram. And the specific heat of nickel is equal to 0.502 joules per Kelvin per gram. So the only specific heat I'd have you memorize would be that of water. Anything else would be given to you, or you'd have the ability to calculate it. Okay, so these two blocks will become the same temperature. As I said before, they're going to want to become in equilibrium. So what we want to do is we want to calculate that temperature final. Okay, so let's go ahead and set this problem up. So we have our system, the two blocks. We have our surrounding. We're going to assume insulated. You weren't told insulated, so nada. All right, so the initial state so different TIs not in contact. And the final state, thermal equilibrium. All right, so we need our energy principle. So the change, so delta E is equal to any work that has been done to it. In this case, this is equal to 0. So we're going to look at the change in energy for titanium plus the change in energy for the nickel is equal to 0. We're dealing with thermal changes, so we're going to use MC delta T. So we have M1 C1 T final minus T initial plus M2 C2 T final minus T initial. Okay, so let's go ahead and differentiate this. So I'm going to call this one 1. I'm going to call this one 2. So we're going to do T2I, or sorry, T1I and T2I. Okay. And you're welcome to use whatever naming structure you want as long as you tell me what it is. All right, so let's break this. Let's go ahead and multiply out. So M1 C1 T final minus M1 C1 T initial 1 plus M2 C2 T final minus M2 C2 T initial 2 is equal to 0. So I have learned from teaching this class for a while that some people have done these equations a lot and some people have never done them before. So I always do one with a lot of algebra in it so that everybody can see all of the steps at least once. Because these are straightforward to solve, but you know, it's just a lot of algebra. Okay, so the reason why I've not subscripted the T finals is because they're going to be the same for each particular setup. So let's go ahead and start doing some factoring out. So we know that T final times M1 C1 That would be for the titanium plus M2C2. So we've factored this out because that's the final state for both. Now I'm going to move everything else over to the other side. So this is going to be equal to M1C1 T initial 1 plus M2C2 T initial 2. Now we're going to go ahead and divide both sides by this here to get T final by itself. So T final is equal to M1C1 T initial 1 plus M2C2 T initial 2 divided by M1C1 plus M2C2. All right, so let's plug in our numbers. T final is equal to 400 grams times 0.544 joules per Kelvin per gram times 550 Kelvin plus 700 grams times 0.502 joules per Kelvin per gram times 275 Kelvin. All of that is divided by 400 times 0.544 plus 700 grams times 0.502. T final is equal to 380 Kelvin. All right, so the thermal energy that was in the titanium was given to the nickel. So if we go back to our original setup that we talked about, we can see that that titanium was hotter and that the nickel was colder at the start. And so that extra thermal energy from the titanium went into the nickel, increasing its total temperature while sacrificing some of the temperature of the titanium block. All right, so as I said before, thermal energy can be difficult to measure, but if you know C, the specific heat for a particular material, then any change in temperature can be implied to be the result of a change in thermal energy. All right, we will stop this lecture here, and I will see you next time for part 2.